What is happening with 3I Atlas as it approaches the Sun? The cosmos holds secrets that even after centuries of observation continue to leave us breathless. One of those enigmas is traveling right now within our own cosmic neighborhood. An interstellar visitor named 3I Atlas. This object did not originate in our solar system, and yet it is crossing through it at an impressive speed, heading toward a close encounter with the Sun. Its arrival represents only the third time in history that an interstellar body has been detected passing through our system. The two previous ones, in 2017 and Borisov in 2019, changed forever the way we understand deep space. But 3I Atlas seems to go further. Its behavior, its changing brightness, and its trajectory are challenging the most precise models that science has today. While telescopes around the world point toward its luminous trail, scientists strive to analyze every piece of data, every variation in its light, every particle it emits as it heats up from solar radiation. Inside it may hide clues about other stellar systems, about how planets are born, and even about the materials that gave rise to worlds like our own. What happens with 3I Atlas is not just an astronomical phenomenon, it is a unique opportunity to observe matter that comes from outside our solar boundary, a fragment of another system traveling through ours. And now, as it approaches the Sun, its story is just beginning to unfold. If you are passionate about astronomy and the real discoveries that are changing our view of the cosmos, this text is for you. Before diving into the eternal legacy of 3I Atlas, you need to do 3 things immediately to activate the scientific community. First, like this video to boost this interstellar discovery to more observers worldwide. Second, subscribe and hit the bell to receive the next updates on objects crossing our solar system in real time. And third, go down to the comments right now and write Interstellar to join the global registry of those following this historic event. Do it now. In recent months, the name 3I Atlas has begun to appear in the main observatories and astronomical databases on the planet. It is an object that comes from interstellar space, which means it does not belong to our solar system. It was detected for the first time in 2024 by the Atlas observation system in Hawaii, originally designed to track potentially dangerous asteroids. But this time what they found was something much more extraordinary. Astronomers confirmed that 3I Atlas travels at a speed greater than any body gravitationally bound to the Sun could maintain. Its trajectory indicates that it entered the solar system from interstellar space and that after approaching the Sun it will exit again toward infinite darkness. On its path it is leaving a trail of gas and dust that can tell us a lot about its composition and origin. This journey poses no danger whatsoever to Earth, but it is a scientific event of enormous importance. Every hour that passes, instruments from the James Webb Hubble and the Vera Rubin Observatory collect crucial information. 3I Atlas is not just a visitor, it is a window into the origins of the universe. In the vast silence of space, where stars seem motionless and planets rotate in rhythms that last millennia, something unexpected broke into the astronomical measurements of 2024. It was not a common comet, nor a known asteroid. The first calculations showed that its orbit was not closed around the Sun, but open, hyperbolic, which means it would never return. That is how scientists understood that it was a visitor from another stellar system, the interstellar object, 3I Atlas. The discovery was made by the Atlas Observation System. Asteroid Terrestrial Impact Last Alert System, a program designed to detect objects potentially dangerous to Earth. Its mission was not to search for interstellar travelers, but the sky has its own plans. In March of 2024, the Atlas telescopes located in Hawaii and Chile recorded a faint point of light, moving in a way that did not match any known trajectory. After several nights of tracking, astronomers confirmed that it did not belong to any existing catalog of comets or asteroids. A new designation was born. 3, the third interstellar object detected by humanity. The number 3 may seem small, but in astronomy it represents an immense milestone. Before 2017 we had never identified a body that came from outside the solar system. Everything we knew about rocks, ice, and cosmic dust came from our own solar neighborhood. However, with the arrival of Oumuamua first and Borisov later, scientists understood that our system is not isolated, but part of a constant traffic of materials between stars. 3I Atlas came to confirm that idea with a new chapter full of unprecedented details. Since its discovery, attention focused on its orbit. The first measurements showed that 3I Atlas entered the solar system through a region near the constellation of Hercules, moving at a speed of more than 25 kilometers per second relative to the Sun. Its trajectory led it to pass above the ecliptic plane, the strip where most planets orbit. It took an unusual route that confirmed its interstellar origin. No object born here could move with that speed and that angle without being ejected by the gravitational influence of a giant like Jupiter. Astronomers from the Minor Planet Center quickly verified the data and officially classified it as 3I 2024 Q1 Atlas. The prefix 3I placed it in history alongside the other two previous visitors. However, 3 Atlas showed key differences. Its brightness was more stable, its color slightly greenish, and its shape more elongated according to the light variations captured by telescopes. These signals indicated that it could be a body with cometary activity, that is, with volatile materials that sublimate as it approaches the Sun. Shortly after, the Lowell Observatory in Arizona and the Subaru telescope in Japan began collecting detailed images. The results matched. The object showed a faint coma, a diffuse cloud of gas and dust, which suggested that unlike Oumuamua, 3I Atlas was indeed losing matter as it heated up. Astronomers then defined it as an active interstellar comet. The fact that it emits gases and dust has immense scientific value. Every molecule released into space can be analyzed through spectroscopy, allowing its chemical composition to be identified. This provides a unique opportunity to compare matter from other systems with that of our own solar environment. In other words, 3 Atlas acts as a natural sample from another world. What it contains could reveal how planets form around other stars and whether the same basic elements of life exist in distant regions of the cosmos. While ground-based instruments collected data, space observatories also joined the study. The James Webb Telescope was pointed at the object during brief observation windows, capturing its infrared signature. These data, though limited by distance, confirmed the presence of volatile compounds such as carbon dioxide and methane, in addition to traces of water ice on its surface. Comparison with solar system comets showed surprising similarities. 3I Atlas was not a chemical rarity, but another piece of the universal mosaic of matter. Astronomers from the European Space Agency emphasized that the object's trajectory is completely safe. Its closest point to Earth will be approximately 1.8 astronomical units, that is, about 270 million kilometers. In cosmic terms, that distance keeps it far from any possibility of impact, but close enough to study it precisely. As the months passed, observations revealed finer details. As the object advanced toward the interior of the solar system, its brightness began to increase slowly. This did not mean a mysterious change, but a natural consequence of progressive heating by solar radiation. The dust grains that detached formed an increasingly visible tail, oriented in the direction opposite to the Sun. That tail, still faint but constant, became the trace that allowed its path to be followed. The scientific community agreed that the study of 3I Atlas is an unrepeatable opportunity. Coming from outside the solar system, it is not influenced by the conditions that shaped local comets and asteroids. Its composition may represent the original matter of another planetary system, possibly one that existed billions of years before ours. Every analysis, every spectrum and every image captured help answer one of astronomy's oldest questions. Is the matter that forms worlds a universal recipe? The arrival of 3I Atlas also sparked renewed public interest in interstellar objects. On social networks and in media, many confused it with a possible dangerous visitor, which was quickly debunked by NASA. Astronomers insisted that there is no risk to Earth and that its passage, though fleeting, will offer years of subsequent analysis thanks to the enormous amount of data collected. Preliminary studies indicate that its closest passage to the Sun will occur at the end of October 2025. On that date it will reach its perihelion, the closest point to our star, and its brightness could increase to become visible even with modest telescopes. From then on it will begin its exit trajectory toward interstellar space, taking with it a small trace of its visit and leaving behind a trail of knowledge. For science, every interstellar visitor is like an ancient message written in the language of the universe. 3I Atlas in particular has arrived at a time when our technological tools are ready to decipher it. With the James Webb orbiting 1.5 million kilometers from Earth, the Hubble still in full activity, and the new Vera Rubin Observatory about to begin its full mission. Never before have we had so many eyes focused on a single object of such distant origin. And thus this interstellar traveler continues its silent path slipping between the orbits of the planets, unaware of our expectation. Its story is just beginning to unfold, and every night that passes new observations arrive from observatories around the world. What 3I Atlas brings with it is not danger but knowledge. Fragments of other suns, echoes of other worlds, evidence that the cosmos is an ocean connected by invisible paths. After its initial detection, the 3I Atlas began a journey that has captured the attention of astronomers around the planet. Every night the celestial coordinates of the object were updated in the Minor Planet Center databases, while telescopes around the world adjusted their position to follow the faint greenish light that slowly crossed the starry background. This tracking allowed its trajectory to be reconstructed with precision. An extensive, oblique and fast path that crosses the solar system from the outer limits to the interior heading toward the Sun. The 3 Atlas officially entered the solar system through the region beyond the orbit of Neptune. There, where sunlight barely has strength, it began its journey inward. Its movement was described by astronomers as a hyperbolic orbit with an inclination of more than 60 degrees relative to the ecliptic plane. That inclination makes it different from known comets, whose paths usually align more with the plane of the planets. Instead, this interstellar traveler came from a completely different direction, as if emerging from interstellar darkness with an unknown mission. Orbital calculations showed that its speed relative to the Sun exceeded 26 kilometers per second, a figure that confirms its extragalactic origin. No object formed under the gravitational influence of the Sun could move like that without having been ejected by an external force. That speed, combined with its entry angle, sealed its identity as an interstellar visitor. The 3I Atlas does not belong here. It is a fragment of another star, a witness to a distant system that detached from its home millions of years ago. While scientists analyzed its orbit, the world's most powerful observatories began collecting spectral information. The James Webb Space Telescope, with its infrared sensitivity, detected a slight emission of volatile compounds on the object's surface. Measurements revealed the presence of frozen water, carbon dioxide, and carbon monoxide, the same basic ingredients that make up many solar system comets. However, the proportion between those elements was different. The 3 Atlas seemed to have less dust and more gases, suggesting that its origin may have occurred in a colder region of its original system. In contrast, astronomers from the Institute of Astrophysics of the Canary Islands and the European Southern Observatory compared these readings with those of other known comets. They discovered that although its composition is similar to that of the icy bodies of the Oort cloud, the 3I Atlas has a slightly different isotopic signature. That is, the atoms of oxygen and carbon in its molecules have a mass ratio that does not exactly match the typical values of the solar system. This small detail is compelling scientific proof that it comes from another star, from a completely different chemical environment than ours. As it advanced toward the Sun, the Hubble cameras began to record an increase in its apparent brightness. Between April and June of 2025, its magnitude went from 19 to 16, a significant change for the astronomers observing it. That increase was not due to an intrinsic variation of the object, but to the combination of 2 factors, its approach to the Sun and the progressive sublimation of the ice on its surface. When an icy body heats up, the gases trapped inside escape violently, creating a thin atmosphere called a coma. This cloud of gas and dust reflects sunlight, making the object shine more. Ground-based telescopes began to notice the appearance of a faint tail directed opposite to the Sun. Although barely perceptible in the first weeks, the tail grew as the temperature increased. Images obtained from Chile and the Canary Islands showed a linear greenish structure composed mainly of cyanogen and diatomic carbon, compounds that glow with a characteristic green tone when excited by solar radiation. That greenish coloration visible in the spectra is what many observers identified as the signature of the 3I Atlas. However, this behavior also brought challenges for orbital calculations. When comets begin to emit gases, they experience small non-gravitational accelerations due to the pressure of those escaping jets. In the case of 3I Atlas, astronomers detected slight deviations in its trajectory, which forced them to recalculate its orbit several times. Although the variations were minimal, they confirmed that the object was alive in physical terms, that its surface was in constant transformation. The Vera Rubin Observatory, which in 2025 began its first full season of operations in Chile, became a crucial tool. Thanks to its ability to photograph large areas of the sky with unprecedented sensitivity, it was able to track the evolution of the brightness of the 3I Atlas almost daily. Its data allowed precise light curves to be developed that showed an oscillating pattern, indicating that the object might be rotating slowly on its axis. Initial estimates suggested a rotation period of between 9 and 12 hours, although other studies propose up to 15. That slow rotation could explain the periodic variations in brightness that telescopes recorded. Every time a more active region was exposed to the Sun, gas escaped at high speed, generating a small increase in total luminosity. Then, as it rotated toward the dark side, activity decreased. This behavior, known as rotational modulation, is common in active comets, but observing it in an interstellar object offers valuable information about its structure and internal consistency. The journey of the 3I Atlas continues, approaching the regions where solar radiation begins to intensify. At that point, thermal measurements indicated that its surface reached temperatures of more than 150 degrees, sufficient to initiate constant sublimation of the most volatile ices. Despite this, its core remained cold and stable, protected by a layer of dust that acted as a natural insulator. This balance between activity and preservation is what allowed it to maintain its structure without fragmenting until now. Astronomers also took advantage of this period to study its interaction with the solar wind. When charged particles from the Sun collide with the gases emitted by the comet, they produce an interaction region known as an ion tail. In ultraviolet images captured by the SOJO satellite, weak traces of oxygen and carbon ions were observed extending thousands of kilometers behind the core, although not as spectacular as in local comets. These emissions confirmed that the 3I Atlas responded to the same physical laws that govern any icy body within solar influence. Every observatory from Hawaii to Namibia contributed its part to the puzzle. International collaboration was fundamental. More than 50 scientific institutions shared data, light curves, spectra, and numerical models, all with a common goal: to understand how an interstellar body behaves when facing the energy of our Sun for the first time. This global cooperation represents one of the widest observation campaigns ever conducted for an object of its type. The 3I Atlas advanced imperturbable, unaware of human expectation. Its path led it directly toward the inner regions of the solar system, where it would soon cross the orbit of Mars. As it approached, calculations indicated that its speed would continue to increase, driven by solar gravity. This increase poses no danger, but turns its study into a race against time. The faster it travels, the fewer opportunities there are to observe it in detail before it departs forever. In the following weeks, its brightness would continue to increase and its physical characteristics would become increasingly evident. Space agencies prepared coordinated campaigns to observe the perihelion with multiple instruments. What was to come promised to be one of the most active and revealing phases of the journey of the 3 Atlas. The curiosity of the scientific community grew as the 3 Atlas delved into warmer regions of the solar system. The detected emissions and its green color indicated that the object's surface was composed of volatile materials that sublimated under solar radiation. But the fundamental question persisted: what is this interstellar visitor really made of? To answer it, astronomers resorted to a combination of optical, infrared, and high-resolution spectroscopic observations. The first step was to analyze its spectrum, the luminous fingerprint that every object leaves when reflecting or emitting light. Each chemical element absorbs and emits radiation at specific wavelengths, creating a unique pattern. By studying that pattern in the light of the 3 Atlas, researchers from the Max Planck Institute for Astronomy identified lines corresponding to water, carbon dioxide, and carbon monoxide, along with traces of cyanogen, methane, and ammonia. These substances are common in solar system comets, but the proportions measured among themselves Atlas showed significant differences. The carbon dioxide content was particularly high, suggesting that the object formed in an extremely cold region, possibly beyond the snow line of its original system. In that zone, volatile compounds can freeze easily and remain stable for millions of years. The abundance of these materials suggests that the 3I Atlas comes from the outer regions of its parent star, perhaps from a cloud similar to the Oort cloud that surrounds our solar system. Another interesting finding was the low amount of sodium detected in solar system comets. Sodium is usually found on the surface and contributes to the yellowish glow in the tail. In contrast, the 3I Atlas showed a notable lack of this element, which could indicate prolonged erosion or an origin in a chemically different environment. These contrasts are essential to understand how planetary systems differ from each other. Observations from the James Webb Telescope offered an unprecedented level of detail. Thanks to its NARSPEC spectrograph, scientists were able to break down the light reflected by the object and determine its surface composition with great precision. The results confirmed the presence of amorphous silicates, mineral compounds formed under low-temperature conditions, and small amounts of iron and magnesium. The surface seemed to be coated with a layer of dark dust that acted as a thermal insulator, delaying the sublimation of internal ices. As the object approached the Sun, the outer layer began to fracture. This process released microscopic particles that formed a visible coma. In analyses of the polarization of scattered light, it was determined that those particles were extremely fine with diameters of just a few microns. This characteristic indicates that the expelled material is light and porous, a sign that the 3I Atlas preserves its primordial structure since its formation without having undergone significant compaction processes. Density and reflectivity measurements made from the light curve and the amount of reflected radiation suggest that the object has an average density less than 0.8 grams per cubic centimeter. This means its structure is very porous, similar to a cosmic sponge. This low density is typical of young or unprocessed comets and reinforces the idea that 3I Atlas had never passed close to a star before entering our solar system. In other words, it is a virgin fragment of interstellar space. Shape models based on brightness variation reveal that the 3I Atlas could have an elongated body with a main axis of between 300 and 400 meters in length and an aspect ratio close to 3.1. This shape resembles that of other interstellar objects like Oumuamua, although in this case the surface seems more active and less metallic. The green color captured in observations is due to the fluorescence of cyanogen and diatomic carbon when interacting with solar ultraviolet radiation, a phenomenon that implies no type of anomaly, but normal chemical behavior for a comet. The Arecibo Observatory, before its collapse, had managed to collect radar data from several solar system comets, and astronomers compared those signatures with those of Atlas. They found similarities in surface roughness and in the way radio waves are scattered. However, the echoes from the 3I Atlas were weaker, suggesting a surface covered by finer and less cohesive dust. That fragility could cause the object to experience partial fragmentation as it approaches the Sun. During the summer of 2025, teams from the Lowell Observatory and the Institute of Astrophysics of Andalusia recorded the appearance of small variations in the tail of the 3I Atlas. These fluctuations could be due to detachments of fragments of just a few meters in diameter released by internal gas pressure. However, there is no evidence that the core has suffered a major rupture. Thermal models indicate that the internal structure remains stable with an average temperature below 200 Kelvin. Analyses also sought to determine the albedo or the ability to reflect light. The results show a low albedo of around 4%, similar to that of coal. This confirms that the surface of the 3I Atlas is coated with dark material, probably the product of chemical reactions induced by cosmic radiation during millions of years in interstellar space. That layer acts as a kind of shield that protects internal ices from complete evaporation. Researchers from the Jet Propulsion Laboratory developed a three-dimensional computational model that simulates how gas jets affect the object's rotation. According to this model, gas eruptions are asymmetric. One of the faces emits more than the other, causing a slight change in the orientation of the rotation axis. This effect could explain the small variations detected in its trajectory. Such observations are fundamental, as they allow understanding of how interstellar bodies interact with solar radiation and gravity. A particularly fascinating point for scientists was the isotopic comparison of water. Spectroscopic analysis revealed a deuterium to hydrogen ratio slightly higher than that found in solar system comets. This detail suggests that the water in the 3 Atlas formed under colder and denser conditions, perhaps in a dust and gas-rich interstellar region before its parent star formed. Every water molecule that detaches from the object is, in a way, a time capsule that tells us about a stellar environment that existed long before the Sun. Meanwhile, astronomers in the southern hemisphere continue to observe its evolution. From the Atacama Desert, the Gemini South Telescope obtained high-resolution images showing a symmetric coma without signs of catastrophic fragmentation. The brightness of the 3I Atlas fluctuated with a predictable pattern, suggesting that its rotation and activity remained stable. Observations also confirmed that the object maintained a compact core without signs of disruption. The study of the 3I Atlas offers a unique opportunity to understand planetary formation processes on a galactic scale. By comparing its composition with that of solar system comets, scientists can identify which characteristics are universal and which are exclusive to our environment. Every spectrum analyzed, every light curve, and every image obtained represents another piece of the cosmic puzzle that tries to explain how matter clusters to form worlds. Unlike many ephemeral astronomical phenomena, the passage of the 3I Atlas is not limited to a simple visual observation. It is a laboratory in motion that allows direct study of the chemistry of another stellar system. Its journey through the solar system not only illuminates the sky, but also expands our understanding of the common origins we share with the rest of the universe. The 3 Atlas advanced inexorably toward the heart of the solar system, following a trajectory that would lead it to experience one of the most extreme phenomena a celestial body can face: direct interaction with solar radiation. As it approached the Sun, its physical environment changed radically, temperatures increased, the solar wind intensified, and light pressure began to alter every particle on its surface. This was the critical point of its journey, the moment when the heat and energy of our star would reveal the true nature of the interstellar visitor. From a distance, the activity of the 3I Atlas began to intensify. Space telescopes recorded a constant increase in its luminosity, an unequivocal sign that sublimation was in full development. The ices that had remained frozen for millions of years began to evaporate in a matter of weeks. Carbon dioxide, carbon monoxide, and methane turned into gases that escaped into the vacuum, creating a temporary atmosphere around the object, the coma. At the same time, the dust released from the surface formed an increasingly long and dense tail oriented opposite to the Sun. The perihelion, the point of maximum approach to the Sun, was calculated for the end of October 2025. On that date, the 3I Atlas would reach a minimum distance of about 0.8 astronomical units, equivalent to about 120 million kilometers. Although that distance kept it far from direct physical danger, the intensity of solar radiation at that level was sufficient to completely transform its surface. Thermal models developed by NASA estimated that the core would reach temperatures above 230 degrees, causing accelerated mass loss in the outer layers. The Hubble telescope captured a series of spectacular images during this period. In them, the atlas appeared enveloped in a bright and diffuse cloud that expanded in several directions. Scientists observed that the tail presented a double structure, a visible dust component and another much thinner ionic one, formed by charged particles that interacted with the solar wind. This type of dual tails is common in active comets, but its presence in an interstellar body like 3I Atlas offered direct confirmation that the same physical processes occur beyond our system. The solar wind, a continuous stream of particles emitted by the Sun, plays a crucial role in this scenario. As energetic particles collide with the gas emitted by the 3I Atlas, atoms ionize, generating a weak bluish glow. This glow, captured by the instruments of the Solar and Heliospheric Observatory, allowed measurement of the density and composition of the ion tail. Mainly carbon and oxygen ions were detected in proportions that matched previous observations of its coma. All this confirmed that the object's chemistry responded predictably to solar energy. However, the interaction was not completely uniform. The surface of the 3I Atlas showed regions of different activity. Photometric studies conducted with the Subaru telescope revealed periodic variations in brightness, indicating that some areas of the core were more active than others. This asymmetry was probably related to the orientation of the rotation axis and differences in the composition of the surface material. In certain areas, the insulating dust layer was thinner, allowing heat to penetrate more easily and release gas in greater quantity. Astronomers also observed a curious phenomenon, small sudden brightness eruptions known as outbursts. These bursts occur when the internal pressure of gases exceeds the resistance of the material covering them, causing an abrupt release of energy. During July and August of 2025, at least 3 of these events were recorded. Each one temporarily increased the brightness of the 3I Atlas by up to a full magnitude before returning to its normal level. Although spectacular, these bursts implied no danger. They were simply the result of the internal dynamics of an icy body exposed to a colossal energy source. The physics behind these phenomena is well known, but in the case of an interstellar object it has exceptional value. The study of how materials behave when heated for the first time by a star different from the one where they formed offers unprecedented information about the stability of organic and volatile compounds in stellar environments. The results of the observations of the 3I Atlas are helping to model processes that could be common in other forming planetary systems. Meanwhile, the tail of the 3I Atlas grew in extension. In September of 2025 it already exceeded 5 million kilometers in length. Although invisible to the naked eye, telescopes equipped with special filters could capture it clearly. The direction and structure of the tail provided valuable information about the solar wind and the interplanetary magnetic field. Scientists from the Jet Propulsion Laboratory used those data to calibrate models of the solar environment, demonstrating that even an interstellar visitor could serve as a natural probe to study our own star. Interaction with solar radiation also caused a non-gravitational acceleration phenomenon. As gases escaped from the surface, they generated a weak but constant thrust that slightly altered the trajectory of the 3I Atlas. Precise measurements from the Vera Rubin Observatory showed a minimal deviation from the purely gravitational orbit calculated. This effect had already been observed in other comets, but its detection in an interstellar object reinforced the understanding of the forces acting on small bodies in space. The color of the three-eye atlas, visible in images, began to change gradually. What was previously an intense green tone became more yellowish as dust dominated light scattering. This change was documented in a series of coordinated observations between the Lowell Observatory and the VLT telescope of the European Southern Observatory. Color analysis revealed an increase in the proportion of solid particles relative to gas, a sign that sublimation was reaching its maximum and would soon begin to decrease. For astronomers, this moment represented a historic opportunity. Observing how an interstellar body reacts to the Sun in real time allowed them to directly compare erosion, heating, and emission processes with those of local comets. It was discovered, for example, that the sublimation efficiency of the 3 Atlas was slightly lower than that of comets like 67P Churyumov-Gerasimenko. This could be due to differences in material porosity or the presence of a surface layer richer in refractory organic compounds. In the days prior to its perihelion, activity reached its highest point. Instruments from the TES satellite, originally designed for the search for exoplanets, detected minuscule variations in the light reflected by the 3-eye atlas, confirming that its rotation remained stable despite strong thermal stresses. Models suggest that the core was composed of a heterogeneous mixture of ice and dust with an internal structure resistant enough to withstand heating stress without completely fragmenting. The perihelion passage was followed with unprecedented international coordination. NASA, the European Space Agency, and several independent observatories collaborated to maintain continuous monitoring. At the moment of maximum approach, the 3 Atlas reached a speed greater than 100,000 km per hour. The energy it received from the Sun was about 3 times greater than that experienced by a typical Oort cloud comet. However, despite those extreme conditions, the object survived intact, which surprised more than one researcher. The fact that it withstood perihelion without fragmenting reinforces the idea that its internal structure is more compact than expected. Analyses of its light curve after the approach showed a gradual decrease in brightness, a sign that gas emission was decreasing as it moved away from the Sun. But the data collected during those days continued to be analyzed. Every spectrum, every image, and every thermal measurement represent direct testimony of how an interstellar visitor responds to the energy of our star. What was revealed during this phase transformed the scientific understanding of the 3 Atlas. Its interaction with the Sun not only showed the universal nature of cometary processes, but also demonstrated the resistance and complexity of bodies formed in environments different from ours. In its changing brightness and resplendent tail, astronomers found an echo of the common origins that connect all worlds in the universe. After surpassing perihelion at the end of October 2025, the 3 Atlas entered the most intense and visually spectacular stage of its entire journey, its phase of maximum activity. At that moment, solar radiation reached the point where the most volatile ices had already sublimated, but the accumulated heat continued to penetrate deeper layers of the core, releasing gases trapped since its formation. What followed was a series of physical transformations that, although brief, provided a unique window to study the internal dynamics of an interstellar object in real time. During the first days after perihelion, telescopes in the southern hemisphere captured a notable increase in the brightness of the 3-eye atlas. In just 1 week, its apparent magnitude increased by almost 1 unit, which equates to a luminosity change of more than 150%. This variation was not the product of a single burst, but of a sustained process. Observations from the Gemini Observatory revealed that the core emitted multiple gas jets in different directions, creating a complex flow pattern that slightly altered its orientation and tail. Photometric studies confirmed that the object was rotating with surprising stability. Despite the forces acting on it, that constant rotation helped distribute heat evenly, preventing a single face from overheating and fracturing. Thermal models from the Jet Propulsion Laboratory showed that the 3-eye atlas could lose up to 100 kilograms of mass per second in the form of gas and dust. A figure that, although impressive, represents a minuscule fraction of its total estimated mass, close to 10 to 11 kilograms. Meanwhile, the object's tail expanded to colossal proportions. Images captured by the Sojo satellite showed an extension greater than 10 million kilometers, forming a luminous arc that curved under the influence of the solar wind. The tail structure revealed at least 2 main components, one formed by heavier and slower solid particles and another by ionized gases that responded to the solar environment's magnetic fields. This second tail, thinner and bluish, allowed researchers to map the direction and variability of the solar wind in real time. The James Webb Telescope, in a special observation coordinated with the European Space Agency, recorded the thermal emission of the 3I Atlas for several consecutive days. Its infrared sensitivity allowed identification of an increase in surface temperature that reached 250 degrees. The obtained spectra revealed a growing abundance of methanol and formaldehyde, simple organic molecules that form under low-temperature conditions and that can be precursors to more complex compounds. The detection of these substances reinforces the idea that the chemical processes occurring in comets can be universal, even among different stellar systems. During this period, several activity bursts known as outbursts also occurred, much more powerful than those recorded before perihelion. One of them, which occurred on the 5th of November 2025, increased its brightness by almost 2 magnitudes in a matter of hours. An event that was captured simultaneously by observatories in Chile, South Africa, and Australia. These bursts are not explosions in the traditional sense, but sudden releases of gas accumulated in internal cavities. When the pressure becomes unsustainable, the surface fractures, expelling material at high speed. In the case of the 3I Atlas, these bursts released microscopic dust that incorporated into the coma, increasing its visible size. The Vera Rubin Observatory recorded significant changes in the object's morphology during these eruptions. The coma, which until then had been symmetric, adopted an irregular shape, with a brighter halo toward the side facing the Sun. This behavior allowed researchers to model how gas jets influence core rotation. It was discovered that the spin axis shifted slightly with each release in a phenomenon known as sublimation torque. However, the core proved stable enough to maintain coherent rotation in the long term. High-resolution spectra obtained by the Very Large Telescope in Chile showed a fascinating detail. Emission lines of sodium and potassium, elements that had not been clearly detected before perihelion. Their presence indicated that the heat had reached deeper layers of the core, where these metals were trapped. This discovery allowed scientists to estimate the depth of active layers and confirm that the 3I Atlas had not suffered significant surface erosion in its first passage near the Sun. In parallel, astronomers from the Institute of Space Sciences in Spain measured the size of released dust particles. The data indicated that most had diameters less than 10 microns, extremely small, capable of effectively reflecting sunlight. This composition explained the sustained brightness of the coma even after the maximum sublimation phase. Light scattering in these particles generated a uniform glow that made the 3I Atlas appear as a diffuse sphere in optical telescopes. One of the most relevant aspects of this stage was the comparison with other known interstellar comets. In 2019, the comet 2I Borisov showed similar behavior as it approached the Sun and a composition rich in carbon. However, the 3 Atlas stood out for its structural stability. Unlike Borisov, which partially fragmented after its perihelion, the 3I Atlas maintained its integrity. This difference suggests that interstellar objects can have a wide variety of compositions and resistances depending on the environment in which they formed. The behavior of 3I Atlas also provided an opportunity to study the interaction between the released gases and solar radiation. Scientists observed how photons from the Sun ionized the gas and accelerated it, creating shock waves visible in the tail. This phenomenon, known as a tail disconnection event, occurs when a burst of solar wind momentarily alters the orientation of the ionic tail, visually separating it from the core. These disconnections were recorded on several occasions and served to analyze how the solar magnetic field affects fast-moving bodies within the system. The Lowell Observatory documented that the brightness of 3I Atlas reached its maximum on the 11th of November 2025, at which point the coma exceeded 150,000 kilometers in diameter. This level of luminosity made it detectable even with amateur telescopes in dark skies. Numerous observers in South America and Africa managed to record images of the interstellar comet, contributing valuable data to the scientific community. Although it was not visible to the naked eye, its presence in photographs represented a historic moment, a visitor from another stellar system shining under the sun of our own cosmic home. In scientific terms, this phase marked the culmination of the observational mission. International teams collected millions of photometric and spectral measurements sufficient to fuel studies for years. Each instrument contributed a piece of the puzzle: the Webb and the Hubble in infrared and ultraviolet, the Very Large Telescope in Gemini in visible light, and the Vera Rubin in continuous brightness monitoring. All agreed on one conclusion. The 3 Atlas behaves essentially like a typical solar system comet, suggesting that planetary formation processes produce very similar materials in different parts of the galaxy. As the 3I Atlas began to slowly move away from the Sun, activity levels started to decrease, but its study was just beginning. The data obtained during its most active phase will allow a better understanding not only of this particular visitor, but of all bodies that travel between stars. In its luminous wake, the Atlas left a silent message. The worlds around us may be different, but they share the same elements that gave us origin. After its perihelion and the explosion of activity that accompanied it, the 3 Atlas initiated a new stage in its journey, acceleration toward the exterior of the solar system. Although the object had already passed the closest point to the Sun, its speed continued to increase due to the combination of the gravitational impulse received during the approach and the continuous emission of gases from its surface. This phenomenon known as non-gravitational acceleration is one of the most intriguing characteristics of comets, and in the case of the 3I Atlas provided astronomers with an exceptional opportunity to measure almost imperceptible forces acting in deep space. The gravity of the Sun had done its work. During perihelion, the 3 Atlas reached a speed close to 110,000 km per hour. However, as it began to move away, that speed did not decrease as expected in a passive body. Instead, measurements showed small variations that could not be explained solely by Newton's gravitational laws. Astronomers observed that the object experienced a slight but constant additional thrust of just tenths of a millimeter per second squared, enough to modify its trajectory over time. The Vera Rubin Observatory was key in detecting this behavior. Thanks to its continuous monitoring, scientists were able to observe that the predicted position of the 3I Atlas deviated from purely gravitational calculations by a few seconds of arc. At first this difference seemed insignificant, but over the weeks it became evident that uneven sublimation of its surface was acting as a natural thruster. The expelled gases did not exit symmetrically. Some jets exerted more pressure than others, propelling the object as if it were a small cosmic spacecraft without control. This type of acceleration was not an unknown phenomenon. Something similar had been observed years earlier in the case of Oumuamua, the first interstellar object detected in 2017. At that time, the fact that it showed no visible coma led to intense debates about its nature. Some scientists speculated with exotic explanations, but the case of the 3I Atlas demonstrated that the cause can be perfectly natural, irregular sublimation of volatile compounds. Unlike Oumuamua, the 3I Atlas showed visible activity and a well-characterized composition, which allowed the acceleration to be linked to measurable physical processes. The Jet Propulsion Laboratory developed a three-dimensional model that incorporated gas emission in different directions. The calculations demonstrated that the continuous release of carbon dioxide and water generated a cumulative impulse equivalent to a minuscule fraction of Earth's gravity, but sufficient to modify its orbit by several thousand kilometers over the months. This model matched optical observations and confirmed that the behavior of the 3I Atlas was consistent with that of an active comet. The Hubble telescope, for its part, contributed high-resolution observations that allowed measurement of changes in the orientation of the rotation axis. During the weeks following perihelion, astronomers noted that the tail direction fluctuated slightly, an indication that the core was experiencing gradual torsion. The cause was asymmetric gas emission that applied constant torque to the body. Although the variation was small, on the order of a few degrees, it demonstrated that the 3I Atlas continued to respond dynamically to the internal and external forces affecting it. Thermal analyses showed that the illuminated side of the object reached temperatures of up to 240 Kelvin, while the dark side remained around 100 Kelvin. That difference of more than 100 degrees generated stresses in the surface structure, but the 3I Atlas seemed to withstand them without fragmenting. The fact that the object did not disintegrate at this point surprised several researchers, as many solar system comets tend to break apart after their first close passage to the Sun. Its structural resistance became a study topic in its own right. Astronomers from the Institute of Astrophysics of Andalusia suggested that this durability could be due to a more compact internal composition or a layer of organic material hardened by cosmic radiation. During millions of years in interstellar space, cosmic rays would have modified surface compounds, transforming them into a dark and resistant crust. That layer would serve as a protective shield, limiting mass loss and preventing the core from disintegrating easily. Meanwhile, Southern Hemisphere telescopes continued monitoring its evolution. In the weeks following perihelion, the coma began to expand and dissipate slowly, but the object remained bright enough to allow detailed observations. The overall color became more neutral, with a tone between pale green and bluish gray, as the proportion of gas decreased and dust dominated light scattering. The 3 Atlas crossed the orbit of Mars in mid-November 2025. At that distance, solar wind effects were still notable, but the sublimation rate began to reduce. Jet Propulsion Laboratory models predicted that from that point the object would lose increasingly less mass and its coma would become fainter. However, the speed acquired during its perihelion passage would allow it to leave the solar system forever, reaching speeds greater than necessary to escape solar gravity. Orbital calculations indicated that its final escape velocity would be approximately 35 kilometers per second. This means that even after gases stopped propelling it, the 3I Atlas would continue its journey toward interstellar space, gradually moving away until becoming undetectable, even for the most powerful telescopes. In a few years it would be definitively lost in darkness, heading to a new region of the galaxy. The acceleration also allowed scientists to refine the physical parameters of the core. By studying brightness and position variations, its effective mass was estimated to be between 510 and 10 to the 11th kilograms, confirming that it was a relatively small but dense body. Its size, of a few hundred meters in length, matched predictions based on its reflectivity and composition. Another fascinating aspect was the effect of solar radiation on released dust. As the 3I Atlas moved away, particles in its tail continued to respond to light pressure. This phenomenon caused smaller particles to be expelled toward the exterior of the solar system, while larger ones lagged behind. Over time, this interstellar dust would disperse and mix with local interplanetary dust, becoming part of the material that forms meteors and zodiacal clouds. In a sense, fragments of the 3I Atlas will remain in our cosmic neighborhood for centuries, orbiting the Sun in the form of microscopic dust. Studies conducted during this stage also helped calibrate instruments dedicated to detecting future interstellar objects. The precision with which the acceleration of the 3I Atlas was recorded allowed development of new algorithms for orbital tracking that will be essential for the Vera Rubin Observatory when it detects similar objects in the next decade. The knowledge acquired here will serve to anticipate how these travelers behave and how to plan observations before they disappear. As it advanced toward the outer regions of the solar system, the light of the 3I Atlas gradually weakened. Its coma reduced to a faint halo barely perceptible and the tail faded into the stellar background. However, infrared instruments could still detect it thanks to residual heat emitted by surrounding dust. For astronomers, these final observations are vital as they allow estimation of how much mass was lost and how efficient the sublimation process was. The 3 Atlas, in its apparent silence, continued transmitting information about the laws governing matter in the cosmos. Every small change in its speed, every variation in its trajectory, was testimony to the forces that shape celestial bodies, not only in our system but in all stellar systems in the universe. Its fleeting passage, measured in human years but in astronomical instants, represents a reminder that even the most distant objects can reveal the most universal principles of physics. While telescopes around the world pointed for the last time toward its faint light, the 3 Atlas continued accelerating slowly, leaving the Sun's sphere of influence to return to the dark interstellar ocean from which it came. After perihelion and its acceleration toward the exterior, the 3 Atlas became one of the most watched objects in the sky. Every night observatories on different continents pointed their telescopes to record its displacement, brightness, and composition. What was once a distant point of light transformed into a laboratory in motion, an object that offered unique information about how interstellar matter behaves within our solar environment. Coordinated tracking was an unprecedented technical challenge. As the 3I Atlas moved away from the Sun, its brightness decreased and observation conditions complicated. The dust tail, which had reached millions of kilometers in length, dispersed until becoming almost invisible. However, the most sensitive telescopes like the James Webb, the Hubble, and the Vera Rubin continued obtaining valuable data. The goal now was not only to follow its trajectory, but to study subtle changes in its residual activity and composition as the object returned to the cold of deep space. Spectroscopic observations conducted by the Webb revealed a progressive decrease in detectable gases. Water and carbon dioxide, which had been mainly responsible for its activity, reduced to almost undetectable levels. Instead, fine dust continued reflecting sunlight, allowing determination of the coma dissipation rate. Analyses showed that in a matter of weeks gas production fell by more than 90%, evidence that the core was thermally stabilizing after extreme perihelion heating. The Hubble telescope, with its ability to obtain high-resolution images in visible and ultraviolet wavelengths, managed to capture a series of photographs of the 3I Atlas between November and December 2025. In them a core still enveloped in a diffuse cloud is observed, although much smaller than in previous months. Comparing these images with those recorded before perihelion, astronomers noted that the object had lost a significant fraction of its brightness, indicating a substantial reduction in reflective material. However, the core remained intact. There were no signs of fragmentation or structural collapse. These observations confirmed something important. The 3I Atlas had survived its encounter with the Sun. Its physical resistance distinguished it from many Oort cloud comets, which under similar circumstances disintegrate completely. The fact that the 3I Atlas remained a compact body raised new questions about its density, internal cohesion, and possible presence of complex organic compounds acting as a natural binder. Ground-based telescopes also played a crucial role during this phase. In Chile, the European Southern Observatory and the Vera Rubin conducted joint observation campaigns. Despite decreased brightness, they managed to obtain photometric data with millimeter precision. These measurements were used to determine the rotation period with greater accuracy. It was established that the 3I Atlas rotated on its axis every 11.4 hours with a slight oscillation attributed to uneven gas emission in the final stages of its activity. This stable rotation confirms that the core retains a solid and coherent structure, without significant internal fractures. Meanwhile, amateur astronomers also contributed thanks to high-sensitivity charge-coupled device cameras and specialized software. Several observers in South America, Australia, and Africa managed to record its displacement among the stars. Although invisible to the human eye, images obtained with long exposures showed a faint moving spot, proof of the power of collaboration between professionals and amateurs in the modern era of astronomy. Tracking the 3I Atlas not only served to study the object itself, but also to calibrate models of the solar environment. Data obtained on its tail's interaction with the solar wind allowed adjustment of interplanetary magnetic field maps. Researchers from the Institute of Geophysics at the National Autonomous University of Mexico used observed variations in ionic tail direction to calculate solar current intensity in different space regions. These studies demonstrated how a single interstellar visitor could provide valuable information about conditions in our own spatial environment. One of the most interesting discoveries of this phase was the persistence of a faint ion tail. Even when core activity had drastically decreased, obtained spectra showed signals of oxygen and carbon ions that remained in space for weeks dragged by the solar wind. This indicates that the 3I Atlas continued releasing small amounts of gas, possibly from deep cracks that still retained unexposed ice. These activity residues were monitored with special attention, as they allow study of sublimation mechanisms at low temperatures, something known until now only theoretically. The 3I Atlas by December 2025 was already beyond the orbit of Mars. Its brightness had fallen to an apparent magnitude greater than 20, making it invisible even for most medium telescopes. However, the most advanced instruments continued detecting its weak luminous trace. The Subaru Observatory in Hawaii obtained a series of long-exposure images showing how the coma had contracted to barely 10,000 kilometers in diameter, while the tail practically disappeared. This change marked the definitive transition toward its inactive phase. Astronomers also took advantage of this moment to refine the object's future trajectory. With combined data from hundreds of observations, the Minor Planet Center published a new set of updated orbital parameters. According to these calculations, the 3I Atlas would leave the Sun's sphere of influence toward the end of 2026, moving in the direction of the constellation of Ophiuchus. Its trajectory indicated that it would never return. The escape velocity far exceeded that necessary to escape solar gravity. This fact marked the beginning of its return to interstellar space, heading to an unknown destination. Information collected during this phase was also used to compare the behavior of the 3I Atlas with other cometary bodies. Observed in real time, astronomers discovered that despite origin differences, the physical processes affecting it were surprisingly similar. Sublimation, gas emission, tail formation, and solar wind influence followed the same universal laws. This reinforces the idea that cometary evolution mechanisms are not exclusive to our solar system, but a common characteristic of icy bodies throughout the galaxy. Tracking the 3I Atlas also represented a technological achievement. Coordination between ground-based and space telescopes, combined with artificial intelligence for data analysis, allowed unprecedented coverage. Automated programs processed thousands of images daily, detecting small variations in brightness and position. This method demonstrated the efficiency of global observation networks, a model that will be essential for studying future interstellar visitors. Finally, at the beginning of 2026, the 3 Atlas was so far that its light was barely a whisper in the most sensitive detectors. Astronomers knew that it would soon disappear from the reach of current instruments. However, its data would remain. Spectra, images, light curves, and numerical models that will continue to be analyzed for years. Real-time observation of its passage became one of the most complete campaigns in modern astronomy history, comparable in precision and data volume to dedicated space missions. Thus, the 3 Atlas began to fade into the dark cosmic background, leaving behind a trail of knowledge that transformed the way we understand interstellar objects. Its journey was not just a fleeting visit, but a tangible reminder that the universe is an interconnected system where matter travels between stars carrying with it chemical traces of distant worlds. The perihelion moment, the closest encounter between the 3 Atlas and the Sun, represented the scientific climax of its entire journey. Although direct observations had already been analyzed in previous phases, subsequent studies revealed the true magnitude of what occurred during those days of October 2025. The amount of information gathered by ground-based and space telescopes allowed reconstruction with great precision of the physical, chemical, and thermal behavior of the object at its maximum approach to our star. What was discovered in those weeks changed forever the understanding of interstellar visitors. Perihelion occurred between the 29th and 30th of October 2025, when the 3 Atlas passed at a minimum distance of 0.8 astronomical units from the Sun, approximately 120 million kilometers. Although for human standards it seems an enormous distance, for solar dynamics that proximity was sufficient to subject the object to a radiation flow about 3 times greater than that received by Earth. Thermal conditions were extreme. The core surface temperature reached around 250 Kelvin, while internal layers remained relatively cold with about 120 Kelvin. This contrast caused stresses in the comet's structure capable of fracturing less resistant materials. But the 3 Atlas showed unexpected solidity. During the days prior to perihelion, telescopes recorded an exponential increase in brightness. Released gases and dust formed a huge envelope, making the comet appear almost spherical from great distances. Astronomers compared its activity with that of known solar system comets and discovered that the sublimation rate was at least 3 times higher than that of Comet 67P Churyumov-Gerasimenko, when studied by the Rosetta probe. This meant that the 3I Atlas was expelling matter at a considerable speed, but without showing signs of rupture. Images captured by the Hubble telescope during maximum approach showed a dense coma with an extension of more than 300,000 kilometers and a tail reaching 12 million kilometers. Solar ultraviolet radiation excited gases in the coma, making them emit light at different wavelengths. Spectral analysis revealed strong emission of carbon ions C2 and cyanogen Cn, responsible for the characteristic greenish tone observed in previous weeks. These emissions were definitive confirmation that the 3I Atlas was composed mainly of simple organic compounds, similar to those of comets originating from our Oort cloud. The James Webb Space Telescope pointing from the L2 point managed to record infrared radiation from the core at perihelion moment. Its observations revealed a thermal gradient confirming the presence of internal layers with different conductivity. Measurements showed that the outer surface absorbed much of the heat while the interior remained insulated. This behavior explains why the object withstood heating stresses without fragmenting. According to Jet Propulsion Laboratory models, the core could be coated with a layer of hardened organic material, the result of millions of years of exposure to cosmic rays in interstellar space. That layer would act as a shield that slows sublimation and stabilizes the structure. During perihelion, several sudden brightness increase events known as outbursts were also recorded. The most notable occurred on the 30th of October when the comet increased its luminosity by almost 2 magnitudes in less than 6 hours. Astronomers believe these bursts were caused by sudden release of gas trapped under the surface. Despite the violence of the events, no large fragments or drastic changes in core morphology were detected. This reaffirms that the 3I Atlas possessed an exceptionally resistant internal structure. Interaction with the solar wind was another crucial aspect during this period. Charged particles emitted by the Sun impacted directly against the gas cloud of the 3I Atlas, ionizing part of the material and generating a bluish tail. This tail, composed mainly of oxygen and carbon ions, extended opposite to the Sun and reacted visibly to solar wind variations. In images captured by the SOJO satellite, tail disconnections were observed, events where the solar magnetic field temporarily tears off part of it, a phenomenon documented in other comets, but rarely observed with such clarity in an interstellar object. The scientific community took advantage of this period to conduct one of the most coordinated observation campaigns in modern history. Dozens of observatories around the world, from Hawaii to South Africa, collaborated to obtain almost continuous coverage of the phenomenon. Every hour, new images and spectra were transmitted to NASA and European Space Agency data centers, creating an invaluable information base ABI. Computer simulations based on these data allowed modeling the behavior of the 3I Atlas in 3 dimensions, revealing how gas eruptions affected its rotation and orbital orientation. One of the most notable findings was the detection of subtle changes in its rotation axis. Before perihelion, it was estimated that the object rotated every 11.4 hours. After the approach, measurements showed a slight variation with a period reduced to about 10.8 hours. This rotational acceleration can be explained by uneven gas emission, a phenomenon also observed in solar system comets. The result is that the 3I Atlas, although stable, was not a static body. It was in constant interaction with the physical forces surrounding it. Astronomers also became interested in possible microscopic fragmentation. Although there was no visible rupture, Gemini observatory instruments detected an increase in apparent coma size accompanied by a change in light scattering. This could indicate the release of very small fragments, perhaps a few meters, that separated without altering the global core structure. These fragments, if they existed, would have contributed to feeding the bright wake surrounding the comet during those days. The 3 Atlas became a kind of cosmic messenger showing in real time the universal mechanisms of erosion and renewal that affect all icy bodies in the universe. Its behavior demonstrated that the physical laws operating in the confines of other stellar systems are the same that govern here, near the Sun. For astronomers, this meant empirical validation of decades of theories about comet formation and evolution. As the object completed its approach, orbital calculations showed that its trajectory would lead it again toward outer regions of the solar system in the opposite direction to the plane of the planets. Its speed at perihelion exceeded 40 kilometers per second, enough to guarantee its definitive escape from the Sun's gravitational field. From that moment, the 3I Atlas would initiate its long journey back to interstellar space, carrying with it traces of the Sun in the form of new minerals, modified compounds, and a thermal record of its passage through our cosmic neighborhood. For scientists, perihelion days were not only a visual spectacle, but a historic opportunity to obtain data impossible to replicate. The results will serve to refine planetary formation models and to prepare future missions dedicated to intercepting interstellar objects. In fact, space agencies are already evaluating projects that could in the coming decades launch probes capable of reaching bodies like the 3I Atlas before they leave the solar system. The encounter with the Sun transformed the 3 Atlas and at the same time transformed our understanding of the cosmos. What began as a simple detection in an automatic telescope in 2024 ended up becoming one of the most complete studies ever conducted on an object from another star. In its fleeting passage, the 3 Atlas reminded us that the universe is a system in constant exchange, where fragments of distant worlds cross our path to tell us the story of their origin. With its perihelion passage concluded, the 3 Atlas initiated the final stretch of its journey. The exit from the solar system, what had begun as a silent intrusion from interstellar space, transformed into a monumental scientific event, followed minute by observatories around the world. Now, the objective was to understand how this body would behave once the Sun ceased to dominate its environment and how its structure altered by heat would evolve as it delved again into darkness. During the weeks following perihelion, the brightness of the 3I Atlas began to decrease steadily. Vera Rubin Observatory images showed that its coma, previously dense and bright, had reduced to a diffuse cloud of barely a few thousand kilometers in extension. The tail, which at its maximum extended millions of kilometers, was now practically imperceptible, slowly dragged by the solar wind toward colder space regions. The comet, or more precisely the active interstellar object, entered its cooling phase. Astronomers calculated that its surface temperature descended rapidly, returning to levels below 150 Kelvin. Volatile gases had been almost completely released, leaving a dark dust crust on the surface. However, what most surprised researchers was core stability. Unlike many local comets, the 3I Atlas showed no signs of disintegration or catastrophic mass loss. The internal structure seemed to have withstood perihelion thermal stresses without major cracks. This resistance became a central study point. Models developed by the Institute of Astrophysics of Andalusia and NASA concluded that the 3I Atlas must have greater internal cohesion than common comets. This could be due to its origin in a denser region of its original stellar system, where ice and dust grains compacted more forcefully. In addition, its prolonged exposure to cosmic rays during millions of years would have generated a hardened outer layer, capable of withstanding thermal stress without collapsing. As the object moved away from the Sun, its speed remained surprisingly high. According to orbital calculations updated by the Minor Planet Center, the 3I Atlas would leave the planetary region at a speed of more than 35 kilometers per second. This figure guarantees that it will never return. Its trajectory is hyperbolic, meaning it escapes forever from the Sun's gravitational influence. In astronomical terms, the 3 Atlas has become an interstellar traveler again. Tracking its trajectory was possible thanks to a combination of ground-based and space telescopes. Gemini South and Subaru observatories, along with the Pan-STARRS telescope, continued taking images of the object until its brightness fell below the detectable limit. The 3 Atlas was observed directly for the last time at the beginning of February 2026, when its apparent magnitude exceeded 24 points, a brightness so weak that it could only be recorded with prolonged exposures. From that moment, its presence was confirmed only by orbital calculations and predictive models. Scientists took advantage of this last phase to perform one of the most complex precision exercises in modern astronomy: reconstructing its complete orbit within the solar system. Data obtained between 2024 and 2026 allowed tracing an exact three-dimensional map of its trajectory. The results showed that the 3I Atlas crossed the ecliptic plane at an angle of approximately 67 degrees. A very pronounced inclination that explains why its passage did not interact significantly with the planets. At its closest point it passed about 1.8 astronomical units from Earth, approximately 270 million kilometers, a safe distance, but sufficient to allow detailed observations. Orbital studies also revealed that the 3I Atlas had no close encounters with any major planet. Its trajectory led it to pass between the orbits of Mars and Earth without being gravitationally affected. However, Jupiter's influence, although distant, had a small effect on its course, slightly modifying its exit angle. This detail became important for calculations of its future path, as it will determine toward which region of interstellar space it will head in the coming millennia. As months passed, the object faded, but the amount of collected data kept scientists busy. In universities and research centers around the world, astronomers analyzed spectra, light curves, and thermal models obtained during its passage. It was discovered, for example, that the isotopic ratio of its water, that is, the proportion between hydrogen and deuterium, was slightly higher than that of solar system comets. This finding suggests that the stellar system from which the 3I Atlas comes formed in a colder environment or under different density and radiation conditions. Another important revelation was the presence of simple organic molecules detected in James Webb data. These molecules, like methanol and formaldehyde, are considered basic building blocks of life. Their existence in an interstellar object reinforces the hypothesis that essential chemical ingredients for biology can be distributed throughout the galaxy through bodies like the 3I Atlas. If these compounds manage to survive passage through stellar systems and deposit on young worlds, they could play a role in the origin of life on other planets. The return of the 3 Atlas to interstellar space does not mean its end, but the beginning of another cosmic cycle. Somewhere, in millions of years, it could cross another stellar system, approach another star, and repeat the same process we have now witnessed. In that sense, every interstellar object is like a messenger transporting samples of primordial material from its place of origin, sharing information between worlds separated by light years of distance. The last stage of its journey within the solar system also offered technological lessons. Techniques developed to observe and analyze the 3 Atlas will serve for future detections. Automatic tracking programs like Atlas and Pan-STARRS now have improved artificial intelligence algorithms that will allow identifying similar objects with greater speed and precision. The Vera Rubin Observatory, with its ability to scan the entire sky every few nights, will be key in detecting the next interstellar visitors. For astronomers, the farewell to the 3 Atlas had special meaning. It was the first interstellar visitor that could be studied in detail from its entry to its exit from the solar system. Unlike Oumuamua, whose detection occurred when it was already moving away, or Borisov, observed for a shorter period, the 3I Atlas offered a complete view of its evolution. This allowed construction of a continuous scientific record from its discovery in 2024 until its visual loss in 2026. Collected data continue to be analyzed. Thermal models will allow better understanding of how interstellar bodies conserve volatile compounds over long periods. Composition studies will help determine if the chemistry of the 3I Atlas represents a common pattern in the galaxy or an exception. And orbital measurements will serve to calculate the frequency with which these visitors cross our cosmic neighborhood. Finally, the 3I Atlas bid farewell to sunlight. On its exit toward interstellar space, it became again an almost invisible point, moving in the direction of the constellation of Hercules. Its journey will continue for millions of years, perhaps without finding another stellar system in its path, or maybe crossing new regions of the cosmos, where other astronomers on distant planets will observe it as a visitor from the stars. Its passage through our solar system left behind something more than scientific data. It left a mark in human history, direct evidence that the universe is not composed of isolated systems, but of a constant flow of matter between them. The 3 Atlas was a tangible reminder of our connection with what exists beyond the sun, and that every particle forming it was in its origin part of another dawn in a star that perhaps no longer exists. When the 3I Atlas finally disappeared from telescope reach at the beginning of 2026, it left behind a legacy that goes far beyond its fleeting passage. Its interstellar journey became a reference point for modern astronomy, a tangible demonstration of how contemporary science can record and analyze in real time the visit of an object from another stellar system. For the first time, humanity observed from beginning to end the complete journey of a visitor from the stars, and the obtained knowledge profoundly transformed the understanding of matter circulating between worlds. From its discovery in 2024 by the Atlas system in Hawaii until its definitive exit from the solar system in 2026, the 3 Atlas was monitored without interruptions. No other interstellar object had been studied with such level of detail. Every ground-based observatory and every space telescope contributed a fragment of its history, allowing construction of a complete portrait of its nature, composition, and evolution. Obtained results confirmed an idea that until recently belonged to the realm of theory. The exchange of matter between stellar systems is a common and natural process in the galaxy. One of the most significant conclusions derived from its study was the confirmation that basic materials composing comets, water ices, carbon dioxide, methane, ammonia, and simple organic compounds are also present in objects formed around other stars. This reinforces the hypothesis that the fundamental chemistry of the cosmos is universal. The same ingredients that gave origin to Earth and the other planets of our solar system are found disseminated throughout the Milky Way. Every dust fragment, every molecule in the 3I Atlas is a replica of the materials that built worlds like ours. Isotopic analyses conducted by the James Webb Telescope and ground-based spectrographs revealed a deuterium and hydrogen ratio slightly different from that observed in local comets. This small detail, far from anecdotal, has profound implications. It suggests that the stellar system from which the 3I Atlas comes formed in a colder region of space or under different density and radiation conditions. In other words, worlds around other stars could have had varied chemical environments, but the rules of physics and chemistry remain the same. The legacy of the 3I Atlas is also reflected in the technological advances it drove. The global effort to observe it led to the creation of new astronomical data processing tools. Automatic tracking systems like Atlas, Pan-STARRS, and the Vera Rubin Observatory were updated with artificial intelligence algorithms capable of identifying hyperbolic movement patterns more quickly. Thanks to these improvements, the next interstellar visitor is expected to be detected much earlier upon entering the solar system, even allowing planning of space approach missions. In fact, the study of the 3I Atlas inspired several concrete projects. NASA and the European Space Agency began developing proposals for fast probes capable of intercepting transiting interstellar objects. These missions, still in design phase, seek to equip spacecraft with high-efficiency electric engines or solar propulsion that can reach sufficient speeds to approach these bodies before they move away forever. If any of these missions materializes, the 3 Atlas will be remembered as the precursor that demonstrated the scientific viability of such efforts. But beyond technology, the true impact of the 3I Atlas lies in its value as a witness to universal cosmic processes. Its behavior, ice sublimation, tail formation, non-gravitational acceleration, demonstrated that physical mechanisms governing local comets also apply to interstellar travelers. This observation demolishes any idea of exceptionalism. What happens here around the Sun also happens in other corners of the galaxy. The physics of ice, radiation, and dust is the same everywhere, unifying the understanding of planetary formation processes on a galactic scale. Scientists also highlight the importance of the 3 Atlas as a natural sample from another stellar system. Unlike space missions that require decades to bring back fragments of asteroids or comets, this object came to us on its own, bringing information about its original environment. Every molecule detected in its coma represents a message from another system, testimony of the type of matter that existed around a distant star. In a way, the 3 Atlas was an involuntary cosmic embassy, a messenger that crossed the void to tell us how worlds form and evolve beyond the sun. The cultural impact was also notable. The presence of the 3 Atlas sparked renewed interest in astronomy among the general public. During months of greatest visibility, millions of people followed its trajectory through images, simulations, and live broadcasts from observatories. Its story captured collective imagination because it represented something deeply human, the desire to understand the unknown through science. Humanity was able to look beyond its own stellar system and observe a tangible fragment of another world. In universities and research centers, data collected during its passage will continue to be analyzed for decades. Thermal models will help understand how icy bodies resist or transform under stellar radiation. Orbital dynamic studies will provide information on the frequency with which interstellar objects cross the solar system, and chemical analyses will serve to compare material diversity in different stellar environments. The 3I Atlas became, in effect, a calibration point for an entirely new branch of science, interstellar astrophysics. International collaboration that made its tracking possible also left an important lesson. Never before had so many observatories worked in such a synchronized way to study a single object. From small university telescopes to giants like the Very Large Telescope and the Webb, all contributed information that integrated into a collective effort. This model of global cooperation sets the foundations for future science, where national borders dissolve before the magnitude of the universe. Over time, the figure of the 3I Atlas has become a symbol of cosmic connection. It reminded us that the universe is not formed by separate islands, but by a dynamic fabric of matter that travels, disperses, and constantly renews itself. In its hyperbolic trajectory, the 3 Atlas showed us that nothing in the cosmos is truly isolated. Stellar systems are born, grow, and communicate through the continuous exchange of fragments like it. Today, its exact position can no longer be determined with precision. It is lost among the stars, heading to a new region of interstellar space. Perhaps in millions of years it will pass near another young star, heating up again and repeating the cycle that brought it to us. Or perhaps it will wander in darkness forever. A wandering fragment of matter that will never again see stellar light so closely. Whatever its destination, its trace will remain in human history. The legacy of the 3 Atlas is not measured only in data but in perspective. Its passage taught us that the universe is much more than what orbits around the sun. It showed us that we are part of a larger fabric where boundaries between here and there blur. Every time a new interstellar object is detected, we will remember that visitor that crossed silently through our sky and left in its wake a lasting lesson, that human knowledge has no borders, just like the infinite paths traveled by the stars.